All right, so today we're going to talk about margins. I do really like this particular SKCD with a reference to the Fermat's last theorem, but obviously the content is of this invented margin node is even more interesting. I remember a few years ago there was this TV series. I think it's called Silicon Valley, where the premise was, oh, the two brilliant kids have discovered um, like a genius scheme to infinitely compress information, and that was, I guess, the sort of the technical background. But if you have learned info theory, you know that's not true. If you remember the little bits of info theory that we talked about in this class, there's also some hints on that. Yes, that cannot be true. Um, anyway, the compressibility of information is a fascinating topic and also very practical. Um, but margin is not the kind of margin we will be talking about today, which will be the first thing that we will define. Um, Luckily, margin doesn't seem to be as loaded as a technical word in the machine learning and applied stats and math neighborhood that we're looking at. It means many different things in finance and economics, which I don't have. I'm not qualified to comment. Anyway, so housekeeping stuff for today is well, there's the semester break coming up. I'm happy with that, and I hope you are too. Um, so, and brief, because I'm happy about that, or because it gives us, the lecturer and tutor team, to have an opportunity to do a bunch of work. Meaning, there's a whole bunch of new assessments being made for the second half. We aim to finish grading assignment one and release it after Easter. So stay tuned for that. Uh, Watch out for a course survey coming your way. I guess championed by the two course reps. Um, and right after the break, we have 2 long weekends. So there's that. So kernel machines. We talked about expressing. So last time, right? So on Monday, we did basically like look at re-expressing regression with kernels rather than data matrices. Um, there were one remaining issue is this computationally it could be potentially O and cubes, whether that's affordable or not. One idea is to make the kernels sparse, meaning that once we learn the classifier, the hope is that we don't have to store the kernel matrix for the whole and compute on the whole data set. Can we actually just remember and compute on the kernel matrices of important data points? So the whole maximum margin classifier can be motivated from this particular angle. Uh, so this first chunk of data will basically construct as support vector machines or maximum margin classifiers. And then we're going to look at two main extensions of it with a side product, the two main extensions, overlapping class distributions and SVM for regression. And on the way to that, we look at sort of what does it mean? Is it similar to something else that we know about, such as logist regression? We'll insert a Lagrange multiplier bit in the So more specifically, this was what we looked at on Monday at a fair amount of depth. So if you use the normal equation for regression, we get this. If we re-express it as kernels, we get this. And kernel the kernel matrix is actually 5 transpose. So in order to essentially flip the order of the matrix multiply, we need to do, yeah, we went through a few other steps to get there. So here are some reflections of what this means, right? So whenever an inner product was used in an algorithm, we can replace it with a kernel with some manipulations. So this is called a kernel trick, which is a useful thing to know. It's one of the takeaways from this week. And the intuition for kernels, it's a kind of similarity measure. And it can be defined over more complex data structures, such as sets, documents, strings, and graphs. The kernel matrix is really a square matrix with dimensions equal to the n by n. In order to compute something like this on the screen, to calculate it is order of n squared. To invert it, it's order of n cubed. So that's bad. So how do we construct sparse kernel machines? So today we are going to venture away from the probabilistic view and statistical view of machine learning. The supervector machines is a non-probabilistic. It's called non-parametric. Let me just say that we vented about this word non-parametric quite a bit last time. The way I look at this is so the number of parameters is not fixed. Before we do the training. It mentions kernel logistic regression. Let's not go there yet. So it says that, well, supervector machine partially alleviates the time complexity problem. So we're not exactly inverting the kernel matrix anymore. So basically don't do this on a large data set. So in general, approximations are needed for a scalable algorithm. So meaning training clonal kernel machines for a really large data set is still a non-trivial problem. For most of this lecture, we sweep that under the carpet. If you're interested, ask me a question afterwards. So coming back to our familiar linear classifier, or linear discriminant, as we covered in chapter 4. We can simply write it as W transpose feature vector phi of x plus b. The training data are n input vectors, x1 through xn. The corresponding targets are now, note that we're using a different representation, is +1 or -1. With this discriminant function, we predicted sign, like class label of a new point is the sign of this discriminant function. Okay, this is slightly different than what we've been saying this semester, where we typically represent class label as 0 and 1s. So some things will change, some things won't. So if we assume that training data are linearly separable, and so there is a hyperplane or linear decision function that separates class 1 from 0, then there exists W that, because the predicted value is the sign of the decision or discriminant function, then if we multiply the target with the sign, then it should always be greater than 0. Right, to see this, so this is the y of x equals W transpose 5x plus b equals to 0. This is a line of the discriminant function being 0. And then on this side, its target equals +1. On this side, its target equals -1. And then on this side, the sign of SGN is sign of y of x is greater than 0, or right. So the sign is +1. The sign of this x in here is -1. So as we can see on the negative side, the two negative numbers cancel each other, and we still get like a positive number, right? So the target here, right? It doesn't say this particular thing is equal to 1. Well, because it leaves up some flexibility in how to represent it. Graphically speaking, if the data set is linearly separable, we basically can imagine drawing these decision boundaries as straight lines, or the decision boundaries are lines that are perpendicular to the wave vector W, and they are straight lines. So if our data set looks like this, there are many hyperplanes or straight lines in this space that separates the data set. We have also said that if we use something like the perceptron on linearly separate data, separable data, it will find a solution. We don't know which one. And where we end up depending on our initial choice of parameters. So this is the question where the intuition for generalization comes in, right? So if these are the training data and there are test data that we haven't seen, which one of these decision boundaries are potentially better for generalizing? You could, like, intuitively, right? So let's not, like, I'm not going to use the generalization lecture to formally argue this, but if I'm using the red line, it may not be so good because it's cutting very close to the blue. You observe the blue. If the observed blue points are representative, then there are essentially blue points in the test data set that might lie close to this. Therefore, they may be easily misclassified by this red line. So in contrast, this pink line might be better. So that's the intuition for margins. The next 30 minutes or so, we're just going to try and formalize this notion of margins. Let me just pause and answer the question from Fei Yang Yu. You are asking about this, okay? Right, so to restate what I said, because there are two things, right? So K as a matrix, cool. So K as a matrix is in matrix of n by n, and then it has its symmetric. So it has about, what's that? Like n plus 1 choose 2 elements that needs to be computed. So that's an order of n squared, right? And inverting an n by n matrix, I'm not going to justify this for you, but it's a well-known, I guess, scaling property in numerical linear algebra is that finding the inverse is an order of n cubed operation. So one intuitive way of seeing this, if you have seen a page rank algorithm, or basically incremental computation of eigenvalues from the largest to smallest, you can see that, well, page rank is some sort of linear algebra iterations that requires about n squares operation. And that finds us the largest eigenvalue. And once we do that, we remove that and do that on the dimension n-1 matrix. So each of these steps requires n squared, and finding all eigenvalues requires n cubed. And then inverting a matrix involves, if we have the eigenvalues, we do the inverse of the eigenvalues, which is order of n, and then we multiply them back, which is n squared. So the whole thing is still n cubed. So that's a very quick workaround about roughly yn cubed. I think modern linear algebra has better algorithms than the one I just described about finding eigenvalues one by one and so on. Yeah, Fei Yang, so it's m cubed plus n squared. I think that's true for the sort of simple algorithm I just described. The modern version, which I think there are faster algorithms where the exponent is not 3, but something like 2.85, something close to 3, but not quite 3. I don't know for sure. So, but n3 and n to the n cubed is still a good rule of thumb for inverting something. Yeah. All right. So we were here. Right. So we wanted to find, well, restate it, state it slightly differently. The intuition is like separators that are far away from either class seems better. And here's a picture of drawing that slightly more precisely. Right? Note that I think in my printed version of the book or the PDF version, the figure is not complete. But basically, there are two data sets. We define margin as the perpendicular distance between the separating hyperplane, which is y equal to 0, and any of the data points. So it's the minimum perpendicular distance that any data point has to the separating hyperplane. For example, this is the distance for this point, this is the distance for this point, and so on. So we can see that across these points, each of them have a different distance, and we pick the minimum, and that's the definition. And the margin is because these data points are separable, so once we have the minimum, we draw that as the blue line and symmetrically around the decision boundary. Then we can imagine all the data points will lie outside of this hypercube or pair of hyperplanes. And the width of this, like, how do you call hyperplane sandwich, is called the margin, right? So actually have the width, the distance, perpendicular distance between the blue plane hyperplane and the red hyperplane is called the margin. So we drew, on the left plot, we drew a bunch of distances, and we find one hyperplane with one particular margin value. The idea of that we wrote down on the last page, that we wanted a hyperplane as far away as possible from all the hyperplanes, means that this particular one is probably not the best that we can find. Because it's wasting some space, right? So you can see that this hyperplane is, well, one margin away from the yellowish points, but to the blue points, it still have spaces to spare. So the maximum margin hyperplanes can probably be moved towards the blue point a little bit by moving. So this margin got bigger, like meaning like the blue points are exactly on the hyperplane sandwich as well, and so is the yellow point. Right. Okay, I hope this geometrically makes sense. Now, how do we do it? We will do it by first taking a look at expressions of these perpendicular distances that we skipped this year in chapter 4. Now it's the right time to look at it. And then we're going to manipulate a whole bunch of optimization questions, optimization problems until we get to a point where it looks simple enough that somebody can solve. So let's dive in. For this particular lecture, I would think the next chunk of content is probably the most, it's a hurdle to get through. After that, once you have that in memory, the other content should be quite understandable. But in case you don't, you can save the other like SVM, regression, and so on for later. Once you understand the first chunk, the rest are simpler, like sort of more or less straightforward extensions. Let's just say that. All right. In chapter 4, there is this figure 4.1, which is informative, I would say. It contains lots of information, so let's look at it. So equation 4.4 is this linear discriminant, W transpose X plus W naught, which is the bias term, or shift term, equals to 0. That is a separating hyperplane, again drawn in red in here. And then for any data point X, the argument here is that y of x, this expression 4.4, gives a signed measure of the perpendicular distance between x to the decision surface. Right. That is, so if we draw, like in this particular picture, the discriminant the decision hyperplane is the red one. W is this green vector. If we only know the hyperplane, we essentially know the direction of W, but we don't know the length of W. And length of W in a lot of cases don't quite matter. But let's say this is the direction of W. And taking any vector X, we can project it down to the decision hyperplane. And what is called this vector X perpendicular is on the hyperplane. And then X perpendicular plus this additional dashed blue part are like, if we take the vector addition, they come back, the result is X, right? So this is what's happening. Right, so let's call this this dash part times right r, right, the length of this part r, right? And then if we plug this expression in back into 4.4, we get W transpose X perpendicular plus this additional dash part, right? And if we rearrange, the X perpendicular is on the decision hyperplane, therefore its value is 0. Then we're left with only the R part multiplied by the W outside and normalized by the norm of W. Right. And the intuition here is R of X. So Y of X is no longer a vector, it's a number, and it is basically scale distance between X and the hyperplane. Remember when we talked about linear decision boundaries, we talked about there was a bunch of contour plots. Where if the boundary is like this, we have drawn contour plots such as this is y equals 0, y equals to 1, y equals to 2, and then y equals to minus 1, y equals to minus 2. So these contours actually are defined by these equal, right, the contour lines of these perpendicular distances. So I hope that makes some sense. I should say this particular figure is a bit dense, and if it doesn't quite make sense, go and read the half a page around it, and that will help. So one associated question that's worth mentioning now is in chapter 7, we're re-encoding the target for classification to +1 -1. Does this change the geometry in 4.1 that we talked about? Not gonna answer that. So leave that for you to think about. If you want, show me a question in the end. All right. So let's say we have been tackling what I call implicitly optimization functions, optimization problems, right? So we talked about this in the Lagrange multiplier section E. We spent one slide on it, which we'll come back to. But generally, like optimization function, optimization problem takes the form of, okay, let's say maximize or minimize something, f of x, subject to a bunch of like functions as g of x, let's say greater than equal to 0. So implicitly speaking, let's say least square solutions to linear regression does fit this bill, except there is, like in this case, the variables being solved are w's. The function being maximized is, let's say, the negative, the log likelihood or negative square error, and there is no constraint. W are just freely, like they can be any real number, right? So it's helpful to think about a lot of machine learning problems as the objective and constraints, and like doing training is solving an optimization problem. So this lecture is sort of also a cultural exposure to the application of optimization to machine learning, although a fairly shallow one. For more of this, yeah, take AML, advanced ML next semester. So the separating hyperplane is y equals to 0, and the distance of a data point from the separating hyperplane is this, as we just talked about last time. So the target is +1 and -1. So if we multiply the target to the function y, the magnitude don't change. Yeah, it's just a function. So this is not the signed distance anymore. So as we said a few slides ago, so target times like sine of y of x, it should be always greater than 0. So this is the unsigned distance. And normalized by the norm of w. So you might ask, the norm of w actually don't matter for where the decision boundary lies. It does matter for how fast these like contour values change, as we also covered in, I believe, chapter 4, right? So the W does affect whether these contour lines are y equals 1, y equal to 2, or 1 equals 1, 10, or 20. For that reason, we are keeping this norm of W around, and in 2 slides, we'll see what we can do with it, right? So if we leave W as unconstrained, right? So in this case, and it's probably like, let's say, some adding. We can express the maximum margin problem precisely as an optimization problem, right, without constraints. So that's nice. And here is what we have. Basically, the margin is defined as the minimum distance of any data point to the separating hyperplane. So therefore, here we go. Minimum over the n data points. This expression here from some, just plug in 7.2, Tn times W transpose phi n plus B, divided by like the norm of W. So we wanted to maximize the margin. Therefore, there's a max sign on the outside, and argmax over W and B, meaning W and B are the thing being solved. Right. All right. So we vary W and B until like this minimum is perpendicular distance thing is maximum. Right. Okay. That's a well-specified problem. How you go about solving that? Oh, it's a separate question. Another nice, well, another, I suppose, common sense or optimization 101 is a problem that's easy to express is not the problem that's necessarily easy to solve. As you can see, if we're being naive about this, like we initialize W and B, and then we run the minimum function over the training set, and then maybe we like adjust W and B in some direction. It's not clear what whether this operation even gives us a direction because the minimum thing operator is not even differentiable. We can do this forever. So this doesn't look like it's easy to solve. I trust most of the class who haven't taken optimization wouldn't have a good intuition about what is easy to solve. So don't worry too much about that. The things you can rely on is, for example, things we know from earlier this semester, things you can compute gradients on are easy to solve. And linear functions and quadratic functions are generally good. So let's just work with that. Yes, there's constraints. There are a whole suite of other problems. Let's work at one small thing at a time. So one thing that's less than satisfying is having to carry around this thingy where the W is part of the variable, right? It's both in the numerator and the denominator. And moreover, the denominator, the norm of W, the L2 norm of W is not even linear. Anything in the denominator is kind of bad. Okay, so let's make an observation. We said we want maximizing the margin, which is the minimum distance. We haven't said how big that margin is, right? So we also said earlier, the norm of W actually don't matter. We can actually change W quite freely if we want, just rescale W, the decision hyperplane wouldn't change. So let's fix one of those, right? We can, if we have two related degrees of freedom, fixing both is probably not a great idea. It will probably get us stuck in somewhere we can't solve things, but we can fix one. In this particular case, if we choose to fix the norm of W to 1, it's not leading to an easy to solve problem either. But it turns out if we fix the margin to be of length 1, this leads to an easy to solve problem. And here's how, right? So the intuition here is that rescaling W and B does not change the margin of each data point, as we said, right? The first intuition is to rescale W and B accordingly. So if we multiply this both by some constant kappa and plug it into the margin expression, they're unchanged because it's both on the top through Y and on the bottom through norm of W. So why don't we just set margin to 1? So this is what's done. So we know the margin is T times W transpose phi X plus B over norm of W. Now we don't fix the norm of W, but we fix the top part to be 1. All right. And for separable cases, this implies that all data points lie outside the margin. What this means is that for all training data points, 1 through n, we have T of n times W transpose phi X plus B is greater or equal to 0. Right. So they are greater to or equal to 1. So this expression is equal to 1 when the point lies on the margin. and they're greater to 1 when than 1 when the point lies strictly outside the margin. So that's intuitive enough. What have we just done, right? So taking a step back, this is nonlinear objective in W. That's what we didn't like about it. And this, it's no longer objective. It's constraints, but it's linear constraints. Okay, so we haven't finished our work yet. We just turned a nasty-looking objective function into a set bunch of linear constraints. Where's our problem? Where's the new objective? So the next page tries to get at the objective, right? So what we have, the first 3 equations we already have from the last page. So because there is at least one constraint that's active, so this is important. We know there is at least one point that lies on the margin, right? For like, so basically, so this is for the point or multiple points closest to decision boundary. We know this holds, right? So 7.4 holds for at least one data point. And when it holds, the minimum term is going to come out to be 1, right? So here's, it seems there is a little bit of magic happens, but it's really basically working out this minimum, working out that we can actually throw away this minimum because the value of this minimum is the value of the margin, 1. And what does that mean? It means if we just inherit 7.3, it means the objective that we are really addressing is maximize the inverse norm of W. That's great. And what this implies is, well, because it's only the norm of W that's in question, that's in the objective right now, we can just flip W to, again, we don't like W in the denominator. Therefore, we can just flip it around and change the sign of the maximization to minimization. And, oh, now we find that we're minimizing the square norm of W, right? L2 norm of W. That looks familiar. We deal with L2 norms plenty, or square errors plenty. So we basically just write it out as a squared norm and stick a 1.5 in front. And now what we have is, oh, this is a quadratic objective in W with a whole bunch of linear constraints. So using our heuristic, linear quadratic functions are good. We're heading in the right direction. So I just take some comfort in that. Solving is still not super easy, as we will see. Let me pause and answer 2 questions. Qinyu Zhao said, if we set margin to 1, is it equivalent to optimize the signed distance? I mean, minimizing Tn sign of this thing. And Fei Yang asked, why is it minimizing with respect to n? Let me answer the easier one, which is Fei Yang's question. So why is this? Why do we have this thing? Let's switch pen color. So this part, it's basically, let me say that on the picture on the right, it will come out to be this particular point. Meaning, what this part does is look over every single data point and its distance to the hyperplane and pick the closest. I hope that helps. I know that the max min sign in combination is super confusing. Especially if you haven't encountered something like this before, the way to look at these things is to, because we're CS class, most of you know how to program. Think of it as like an inner loop that does the minimization and the outer loop that does the maximization. In this particular instance, yeah, and they're nested. Yeah. You can because if we think about them as loops, the inner loop is naturally discrete because it's looping over all the data points in here. The outer loop is what's problem here, because it's not looping over a discrete set of values W, but to conceptualize the question, you can think about it as looping over possible values of W. Just imagine you have fine enough grids for W. Ignore cursive dimensionality, ignore the real space. If we just want to conceptualize the problem, think of that as, maximizing, or basically looping over all values of W and B and find the maximum. Of course, it's not how we solve it, and we now have linear things and quadratic things. We would want to actually do gradients, being able to do gradients and make use of them. But that's a separate topic. So back to Chingy's question. If we set the margin to 1, in this particular case, it's actually not like the margin per se, it's the unscaled margin. So the margin is, so margin is this W transpose phi of X plus B over the norm of W. So the unscaled margin 1 is what we're fixing. What you write in the chat, so actually T times the sine of Y of X, this is always 1, because sine function takes, or actually, well, when Y is exactly 0, the thing is 0, but yeah, so this thing takes +1 - 1, and T is +1 - 1. And their signs change together. So no, we're not minimizing or maximizing the unsigned distance, if that helps, or with the sign function in the middle. What your question imply actually is, if we're setting the top part of the margin to 1, and our original mission is maximizing the scaled margin, right? Then it's exactly what we're doing on this particular slide. Is it says, this thing vanishes to 1, and we're just maximizing the norm of W instead. I hope that helps. Okay, if not, shout at me after a few slides, a while. Yes, this part is a little bit confusing, I would say. When you see it for the first time, it takes a little bit of time to sink in. But I saw it is right. So in hindsight, it is a nice trick to transform optimization problems. So for one that is, it has 2 loops and it's not linear, it has stuff on the top and bottom, to something that looks like it has linear paths and quadratic paths. That's nice, right? Anyway, now let's look at, go towards the direction to answer how we can potentially solve this. how should I say it? So actually, in terms of teaching SVM, there's several ways. Like, okay, so let me say, like one, like you could do like an SVM without finding support vectors. So you can imagine a baby version of kernel machines is just to do the k times lambda in inverse. Like implement that in NumPy and you're done. And it's actually correct as well, I believe. Right. So it's, or let me just say brute force. And then there's a whole bunch of variants on how do you solve this SVM thing. Because we know how to solve quadratic objectives or how to minimize those. That we've trained a lot in this class. We haven't trained a lot in like, oh, what do we do when we are dealing with a quadratic and convex objective function, which is nice, but we're now solving it in a high dimensional polytope. Like essentially a polygon, but in high dimensions, right? So we run into these edges of this valid region. What do we do? Yeah, it's perhaps worth drawing that somewhere. Basically, what we're doing is, let's say this is a high dimensional polygon in some arbitrary shape. The shape is also convex, and then on this polygon thingy, there is this quadratic function, right? So this is, I can't draw in 3D, but it's a sort of a quadratic ball living in there. Like you're like, okay, how do we solve this? Before we talk about that, let's talk about Lagrange multipliers and optimization a little more. This slide we have seen. I believe I fixed it this time around. But anyway, we, as a reminder, because it's a few weeks and these things we forget. The 101 of Lagrange multipliers is that if we have, we're maximizing function f of x subject to equality constraints, which is essentially this red curve in high dimensions, we can transform this thing using Lagrange multipliers by doing fx plus lambda of gx, and the minimum local maximum of L will be the local maximum of f. In this case, it's obvious because gx is 0, but geometrically, what this means is that the gradient of the two, right, because it's the local maximum of L, or the stationary point of L, the gradient, which is gradient of x plus lambda gradient of g, is 0, and then the gradient of f and g are either perpendicular or in like sort of opposite with each other, that are also sort of perpendicular to the g function, the constraint function g, at that particular point, which is nice. Okay, so you say, well, that's optimization problem with equality constraints. We don't usually sort of try to solve a minimize a function on the curve. We were, like 2 slides ago, we were looking at this polytope, right? So what about, maximizing a function on some region, basically this area enclosed in this red curve. So anything in this yellow region is also valid. Right. I believe like the, so compare this to the version in the book. There might be a typo somewhere. I forgot where the typo was, but let's say maximize f of x and then subject to g of x greater or equal to 0, which looks enough like what we were looking at, except in this picture, the region is not convex. It's a PV shape, but as rule of thumb, convex shapes and convex functions are better objects to deal with. What this means is we can write out the Lagrange in the same way, and we are maximizing the Lagrange yeah, one note is these things are typo prone because of the signs of the Lagrangian, right? The sign in the middle, whether we're maximizing or minimizing, and the objective max min and the constraint direction also all need to line up. Uh, in this class, we're not probably gonna expect you to get all of these things right. That's what you do in AML. Right. So there are two cases when we're at the local, like stationary point of L. What are these two cases? One is one case is basically, the points lie inside the constraint region. Basically, the points are somewhere here in yellow. That means g of x is greater than 0. This is called the constraint is inactive. What that means is if gx is greater than 0, lambda must be 0 for the value of L of x to equal to the optimal value of f of x. And it must be like stationary point, local stationary point of f of x as well, because it's a stationary point of L, right? So the second case is g of x equal to 0 when the optimal point lies on the boundary. That means, like, okay, lambda is no longer 0, but the whole derivative of L, the Lagrangian, is still 0. That means the gradient of f is sort of minus lambda, the gradient of g of x, and lambda is greater than 0. All right, so that's a mouthful. Expressed formally, this is called the KKT condition, a well-known KKT condition optimization. We'll talk about history of this a bit in the next slide. But basically, these three expressions, these three equalities and inequalities, must hold for the optimal solution of the Lagrangian. This is to say, okay, gx greater than or equal to 0. This is uncontroversial. It's part of the original constraint. Lambda is positive. This is, we can define this in the Lagrangian. And then lambda times gx equal to 0. This is basically the shorter expression of what we just said of constraint either being active or inactive. Basically, either lambda is 0 or gx is 0, meaning the point is on the boundary. Okay, so that's called the KKT condition, and we will need it a few times in this lecture. So the historical note was interesting, I thought. So Lagrange is a French mathematician who made a number of contributions in a few areas of mathematics, moved to Berlin, moved back to France, and narrowly escaped the guillotine in French Revolution. So what's remarkable between scientists then and now is it's the breadth of contribution they can make to the fundamental, to many different areas. People nowadays can rarely do that, maybe because the whole body of human knowledge has grown so much. And also they were making all these contributions at like taking risks for their life, whereas we are not, most of us. The vast majority of us are not, which is a luxury. And another note about KKT is, yes, it's 3 people. As the funny thing about optimization is a lot of important results are named after multiple people because they've either collaborated, it's in the first case, Kuhn and Tucker, but Karush actually discovered it a lot earlier, like 12 years earlier in his master's thesis, which is remarkable. And Like it also is a reminder for us on how much faster information transmission has become in the age of, I guess, academic search, Google Scholar, and so on. It's unthinkable to think about rediscovering a result after 12 years. Anyway, so that's a detour, and let's now come back to our problem that we outlined. Took some pain in sort of transforming to a form that looks nice. Quadratic objectives, a half of the 2 norm of W, and then linear constraints. So we talked about Lagrangian in the last 10 minutes, so let's just write it out. So the objective function, copy it as is, and then we have, so these alpha n's are the Lagrange multipliers. So the thing about Lagrange multipliers is that there is one Lagrange multiplier per constraint. Right, so this is what it's said. The shallow intro to Lagrange multiplier brushed that under the carpet, but now we're using it, right? So for each of these n constraints, one for each training data point, we write the Lagrange multiplier as alpha n's or ANs. And because this is minimizing the Lagrange multipliers, so it either needs to be negative or we put a minus sign in front of it, and this is the case, right? So because we define the alpha and ANs to be non-negative, then the sign in front of this whole thing needs to be negative. And then we just move the one to the other side and stick the constraint in there, right? Okay, so this is Lagrangian for this question. And if we, okay, this Lagrangian now is over W, which is unconstrained. We know how to solve that. We could just set the derivative with respect to W and B to 0. What do we get? We essentially get W equals to essentially alpha n Tn times 5xn. It's and then furthermore, alpha n, An and Tn, like the inner product of these two are 0. Meaning these Lagrangians, they're essentially weighted by the class labels are 0. Very interesting. Did that solve our problem, right? You might ask. But we have this quadratic Lagrangian. We calculated the derivatives. So what's left are the ANs. The problem is we still don't know what the ANs are. The solution of W expressed in ANs is like a linear function. That's A's, but what are they? In order to do this, we need to essentially substitute the W out. And this slide does that. Before we go in there, let me clarify a thing, right? So this is called the dual representation, where it's sort of the optimization problem expressed in the Lagrange multipliers, more rather than the original variables. Studying and coming up with dual representations itself in optimization is a big topic that will take you, I know, a solid 2 while to grasp in AML. So I would say in here, what we expect is basically the cultural exposure. So if you don't feel like you can come up with the dual problem yourself after this lecture or looking at it, don't worry too much. This is here, the name dual representation is here so that you have seen this word at least once. But this is what we actually do, right? Again, these the first three equations are from the last page. Nothing new there. And now what we do is we already expressed W in the A's. Now we plug that back into the equation, meaning, yeah, basically substitute W with 7.8 and then try to use this identity we discovered in the process. Then we get this L tilde where the variables are the A's or alphas, and it looks like this. So you may say, oh, how do we get that? Let me say that I have a page written out for you, which is this page that I'm not going to work through. Hopefully it's straightforward enough after our kernel lecture, and just basically it's manipulating these. So this is it left for your for reading. Right now, let me just say that trust me, if we plug this in, but this derivation is not in the book, that's why I wrote it out. If you can't read it, also shout at me. But basically, yeah, trust me, I trust this expression. And subject to the following constraint, we said the alphas are non-negative, and the constraint here is weighted by the labels, they sum to 0. Meaning like the weights, the Lagrange multiplier weights on each example, like because in each training example there's a constraint, so we can intuitively think about this particular A's as the weights on each example. So the good thing is in this constraint we can interpret as the combined weights and or the, let's say, total weights of class +1 and class -1 are equal. I would just take the ones with Tn equals -1, move them to the other side. So that's a nice interpretation. And then what is 7.10 actually? So this is the first term is a linear term, so this is quadratic. Meaning we have the A's multiplying each other and there's A squared somewhere. So the A's are variables, and so these are basically training data, right? You say that, well, at the beginning of this lecture, you promised us sparsity. And in the pictures, you keep promising, I keep promising you guys sparsity, like the hope here, I'm saying it's a hope, it's not a guarantee so far, is that lots of these ANs are actually 0 and therefore leads to sparsity. Okay, we shoved stuff in our tool bag that we haven't used yet, which will give us sparsity, or at least the intuition of it, which is the KKT conditions. Okay, after this slide, we'll whip that out. So, well, top of this slide, 7.10 again, with the same constraints we written out. And then if we have solutions, right, this is a biggie. Assume we have solutions for A. And you ask me, oh, how do we get it? This is, let's say, obtained using either a standard quadratic program solver. There are many good ones. Like some are in SciPy, some like a standalone. I'm happy to recommend, or a customized SVM solver. So just imagine you can chuck this into a black box. Take this whole thing, take this whole program, express it in the way that the solver understands, and then alpha comes out. All right. Once given alpha, you can have B's, which are similar to the linear, like regression and classification bias terms. So it's basically the difference, like the average difference between the target and the prediction function. Yeah, so that's less important. I'm glad I told you about the solver. Now let's look at the sparsity of margins. Right, and we also have the notion of margins. You're like, what happened to that? So KKT conditions will give us this what's so-called support vectors. So we make predictions via this function, right? So we're still assuming that we have these phi's. In reality, we never need these phi's, but it's assuming that we symbolically have them. And we also don't have the W's, we only have the alphas, right? So if we substitute W equals alpha and Tn times phi of x summed over all n, we get back this. So this is the kernel trick, right? In here we use the kernel trick. Basically, this and this phi's, they are inner products, right? So we were taking inner products of them, therefore they lead to this kernel term. Kernel trick in action here. Yeah, the alpha and Tn term is just copied down here. And this is how you once assume some solver gives us the alphas, then we're essentially just making predictions by doing the signed weighting of kernel values between the new data point and all of the existing data points. So it's not that like this, what this implies is that ignore training points with alpha n equal to 0. If there are lots of training points with alpha n equal to 0, then we can ignore a lot of them, which leads to sparsity and the desired outcome. So is that actually true, right? So let's go back to the primal, the Lagrangian of the original problem. So half of the square norm of W minus this Lagrangian set of Lagrangian term. So KKT condition determines, yeah, look, alpha and negative. This is by definition. The second line is just the original constraints. The third line is, oh, it's either one of them must be 0. Let's just say, so what the interpretation is either alpha n or this like Tn and xn minus 1 is 0. What does that mean? So geometrically, so for these guys, alpha n equals 0. For these guys, alpha n equals to 0, because this Tn times yn term is greater than 1, right? For these guys, the ones that lie on the margin, the alpha n greater than 0. So for this particular picture, if you have a data set that looks like this, right, the derivative is, in this example, geometrically we can already see only 3 alpha n's are greater than 0. And that's good news. So yes, we're dealing with kernels, but we're not dealing with order of big N's cubed computation. And that's why support vector machines is Also conceptually so attractive and beautiful because we can obtain it using a principled optimization framework. And then we have these nice geometric intuitions that can hopefully tell us, well, how many support, there's only a number of support vectors we care about. What this also means is that this is called a quote-unquote non-parametric classifier. Basically, if we have a huge data set, and at the end we have a small number of support vectors, when we make predictions, we can throw the rest of the data set away and only remember the support vectors. That's all. And on top of that, there are nice theoretical properties. Like I'm just gonna make a note. Guarantees. So in the serial lecture or generalization lecture, we kind of said VC dimensions is the same via the VC dimensions. I think one of the planned assignment questions around VC dimensions. So this is a hint that some of this is coming. And you may say, yeah, we talked a lot about kernels, and linear kernel was not the thing that we use, right? In the last page, this is linear, right? So this is a linear separation space. So what about nonlinear kernels? What about support vectors in nonlinear kernels? And this is an example of that. So if we have Gaussian kernel and the separating boundary is this yx equal to 0 is this dark line, then we can have support vectors lying more or less all over the place, and these are the contour lines, right? So these are the, I don't know which one is +1 or -1, right? So these are the, I guess, margin planes, where the green circled points are the support vectors. So that's nice. In this particular example, it's still sparse. We are like essentially throwing away or able to forget any of these points that are not circled. All right, so that's I think we have introduced a few new main ideas. One is the geometry of margins. The other one is basically constructing the max margin classifier by transforming optimization problems. And we also used KKT conditions to explain to you why SVMs are sparse. Now let's just reuse these ideas to look at two important extensions. One is, what if the data are not linearly separable in the kernel space or in the feature space, which happens a lot in reality. And then what about regression? Classification and regression always go hand in hand. Like SVMs are also good regressors. So here is the SVM optimization problem again. In order to extend it, let's just look at it in a different light, right? We've been doing this a lot in this class, and right now the different light is, how about we look at it as a different objective function? So, right. So the equation 7.19 is basically the Lagrangian rewritten, but with the lambda put in front of the W rather than the separate lambdas put in front of each constraint. There's a good reason why this is done like this, is because this objective function E of infinity is basically, it takes values 0 and infinity. So basically, the traditional SVM deals only with linearly separable cases. Basically, is the point is on the margin or outside, it's 0. And if the point violates the margin, it doesn't know how to deal with it anymore. And like implicit objective blows up to infinity. Any gradient-based method that our QP solver is using is, yeah, it's not gonna work. So what's the fix for that? Right, so infinity is an open. So building on to our picture earlier, I do believe there should be a data point in each of these, in whichever class, I forgot. The rendering the book is not great. Actually, this should be the other class. It should be blue. This one should be blue, probably. So we introduce what's called slack variables. We can say that if we don't want to say that once it violates the margin, the cost for doing that is infinity. We can say there is a associated cost for violating the margin. And because we're operating in this geometric like distance space, clean L2 distance space, we can say the cost you pay for violating the margin is your distance to the margin on the correct side of the hyperplane. Meaning that, for example, for this point, C is 0, for this point it's 0, but for these ones, the C is for the misclassified point, because the width of the margin, normalized width or unnormalized width of the margin is 1. So for this one, the cost we pay is greater than 1, for this one is less than 1, and so on. All right. So that will allow us to have some data points that violates, like, that lies sort of, that sneak into the hyperplane sandwich. All right, flexibility is good. So now what have we done? We just replaced the constraint, right? We were working with these particular constraints. Now they just become like t times y. It used to be greater or equal to 1. Now it's just greater or equal to 1 minus the slack variables. And the slack variables are greater or equal to 0, are non-negative. All right. So again, what have we just done? What we did was to take the SVM with hard margins version that's repeated over many slides now and transform it into a problem with soft margins, right? So we've covered 7.20 as the sort of the constraint incorporating slack variables. We covered this one because we said slack variables are non-negative. So what do we do with the objective, right? So this pi is the same. The 2 norm of W is the same. And now we know slack variables are bad, so we're just gonna penalize it. We wanted to minimize the total violation of margins, weighted by some factor C. And C controls the trade-off between the slack variable penalty and the margin. The objective tries to minimize this total slack. This is the term that represents total slack across the whole training set. And the trade-off, like, we simply minimize all total slack and set that to 0, then we're not allowed any violation of margins. So similarly, if we allow these C variables to be anything, then they will incur a penalty in the optimization. So that's neat, right? It's a principled way for us to spell out trade-offs. like working with trade-off is what engineers are good for. So yeah, optimization is lovely because of this reason as well. Also, interestingly, so C is greater than 1 if the point is misclassified. Then this sum can be also interpreted as an interpretation of misclassified training points. Right? So another benefit is these slack variables give us sort of a rough diagnostic on how well the training has converged. That's cool. So now we just repeat the soft margin optimization problem here. This is from the last page, nothing new. And similarly, we write the Lagrangian for this particular problem. It basically involves, this is the objective part, nothing new. And this is the same Lagrangian multiplier as the hard margin SVM, right, with the addition from hard margin inversion. We just, with the slack variables in there. Now the additional thing is, now we know that for Lagrangian multipliers, we need to have one term per constraint, right? Because these CNs, they each have their own linear constraint, or basically just a bound constraint. We need to have each of these C's need to have their own Lagrangian multipliers. So, okay, so this is the long, this long expression. If we basically take it apart, it's nothing but assembly of things that we know. So this is the Lagrangian, and what are the KKT conditions, right? So here are the KKT conditions. So these two are not the mu's, right? These two, they are the definition of Lagrangian multipliers. Nothing new. And these two are the original constraints. And the two crucial ones is, so it's either alpha n or this term are 0, and either mu n or the slack are 0. That's what the way we read KKT conditions, right? So on the first one, we simply read alpha n is 0 when the point is correctly classified and is outside the margin. And alpha n is greater than 0 when xm is classified or not misclassified but lies inside the margin. Okay. So we just use KKT again, and we wonder, right? So we change the whole optimization problem. So after we train the SVM, how do we make predictions, if anything? And solving it, so this is basically similar. Don't need to go into the details. But what changes that actually there is a lot, like box constraint on our alpha n as well. The change from the separable case is that alpha n are now bounded. So this C is called a hyperparameter, which we have to set before running the training algorithm. the prediction function is exactly the same, but now all of the support vector weights are bounded. You may say, oh, so what is a good rule of thumb of choosing C? If this is the only hyperparameter you set, you do what's called grid search over a range of values in usually log space. Just bear in mind whatever C you set, it sort of sets sort of a scale bound for the alphas as well. And note that this is no matter what kernel function we choose, right? So in here we can use, right? So in here, whichever kernel we plug in, the prediction function is the same, right? Linear, polynomial, RBF, graphs, and so on and so forth. So you say, oh, that's nice. It seems to, like, you could even think that, oh, SVM classifications seem to be strictly better than like a lot of linear classification we learned. So are there, like, there is no free lunch in this world. What have we lost? Okay, before we talk about that, let me address Fei Yang's question. It's a good question, right? So we don't, like, so okay, we don't need to, so this, what, how should I, way I should say this is, okay, so informally we need a little case, like on the training point, little case for x ends when alpha, when n are the support vectors. We don't need big K as a matrix. So in a sense, yes. Once you have trained the classifier, we don't, like the data file you actually store, or the model file you actually store for your SVM model doesn't have the entire grand matrix in it. Because we, as we said a few slides ago, ideally we kind of forget most of the training points and only for the important ones, the support vectors. That's nice. Then, so this is basically the testing time, prediction time. So training time, what happens? There is no short answer for this, unfortunately. So in order to select the correct support vectors, this is what's done under a QP solver, either generic or custom. You could, for example, there is, let's say, there's this acronym called SML, sequential, something optimization, I forgot, which is a famous solver for SVM. The simplest version of that is to take essentially 2 points at a time. Basically take rows or the submatrix of the grand matrix at a time and then adjust the weights until it's optimum. But that doesn't mean that we're not touching the whole grand matrix. That doesn't mean that like you don't need to pre-compute the whole grand matrix and store it in your memory when you do training. There are many computational tricks on like how you do that faster and so on. There's a whole subfield that has been active between, let's say, 2002 to 2010, devoted to the optimization of SVMs that I'm not gonna do justice to. But I guess you get the idea. Let me just say that like you can use algorithm such as SML, which I think is mentioned in the book, and you may still need to compute and store the entire K. The different solvers also have different caching strategies and so on. There is one particular scholar, like for example, C.J. Lin in National Taiwan University was known for making a fast and reliable like SVM solver. Author of libSVM has like tens of thousands of citations. Almost every single machine learning practitioner uses that. Prior to 2012, the time saving comes, Fei Yang, good question, from the fact that we're not inverting it. You can still compute it. Right, SVM regression, let's just hold on and we'll get to that in the next 10 minutes, I believe. Right, okay, so here are some criticisms about SVM. The output of decisions, they're not posterior probability. If you want a probability, you need to do some other things, such as what's called plus scaling. It's basically retrofitting a sigmoid function to it. Let's not get into that. If you want to do more than 2 classes, because this is learning a discriminant function exactly at 0, it's not, yeah. We talked about this designing discriminant functions in the classification lecture. So the dilemma there applies here. But because this is explicitly learning to discriminate 2 classes, we cannot use the discriminant function trick to just learn k different functions, because there will be no negative class sort of discriminant. Like that's principle, right? So there's some problem here. Right, so we have to find the complexity parameter C. Don't worry about the new, it refers to a different kind of SVM that we haven't covered. It's in the book. Right, the nice thing is the prediction is expressed in the linear combination of kernel functions that are centered on the training points. And the kernel matrices are required to be positive semi-definite, which can be seen as a limitation. All right. So, right. So the derivation of the SVM in the Bishop book provides a nice example of Lagrange multiplier in optimization. There is a dual formulation, but yeah, don't torture yourself too much on it. Let's say for this class, maybe we'll focus on Lagrange more and just know that we can have the dual as a sort of tool to help us actually solve the problem. So there are much more solvers things. So there are some, some solvers that work in the dual space. It has been shown that like you can derive efficient solvers in the primal space as well. This is one of the many possible like papers that's being written on the subject. It is a good one though. So before we talk about regression, let's look at logistic regression and whether SVM has any similarity to it, right? So let's first look at a picture. So remember 2 slides ago, we were looking at this, like we were re-expressing SVM with this infinity error function. But what we have been doing, right? So SVM, so the constraints that T and Yn is greater, let's say the higher constraints than 1, actually correspond to this what's called hinge loss that has been studied a lot since the fast development of SVMs. It's basically the positive part of 1 minus Yn Tn. What does it mean? It means when this bracket and positive means when the things in here are positive, it takes the original value. When the things in here are negative, it's 0. So basically x positive is x x is greater or equal to 0 and 0 when x is less than 0. Okay. So graphically, what this translates to, because it's 1 minus y and tn, it's actually flipped. So yeah, so those actually x bracket positive is the Redel function that everybody now knows as. And this is just a flipped Redel and moved by 1, right? Because of right. So that's easy to understand. So this is the equivalent SVM objective function plus an L2 normalizer. Yes, we also cheekily just moved lambda to be in front of W. So we are familiar with this. Now, if we look at the logistic regression error function, it is yeah, this red line. And if we look at the square loss, it is this green line. So we can kind of see that, well, the SVM classifier loss function is somewhat similar to logistic, but not very similar to the square loss, which we love in regression. Analytically, these are the expressions. So in linear regression, we use square loss. It translates to that green line. In logistic regression, if we minimize the negative log likelihood, this is what we end up with. And in support vector machines, we do hinge loss. And they all have similar forms, right? Plus the regularizer, norm of W at the end. So if we take the hinge loss or the flipped and shifted Redel as an inspiration for designing an objective function for regression, here is what we can end up with. Right? So we can say instead of having a like margin sandwich on the hyperplane, now for regression, because the middle of the sandwich is no longer flat, let's just try and have a tube where the width of the tube, right, the tube is sort of a curve that goes around a high dimensional curve that we try to regress on. And we are going to make the loss what's called epsilon insensitive, meaning that when we try to do regression, the regression error within the high dimension, like the epsilon tube, we don't care about, which is the flat part of this curve. And then we make it go up, like once the error is outside of the tube. So this is called the epsilon insensitive error function. And this, well, in terms of shape, it looks somewhat like the quadratic, the square loss. So we kind of said, well, the hinge loss looks like the log loss. Now we have something that looks like the quadratic loss, despite it's linear on either side, right? That's probably good enough. So this is 7.50 is the square loss. For L2, yeah, square loss. And this is the SVM regression loss, epsilon insensitive regression loss. And this is the exact expression of the regression loss at the bottom, which after having the graphical intuition, you don't need to consume that in real time. So how do we actually implement this, right? It needs like one more set of slack variables, because now we're dealing with, say, the prediction function y is this curve in the middle, and then we have y plus epsilon and y minus epsilon characterizing the epsilon insensitive tube, and then we have so different from classification, stuff that's outside the tube is actually bad rather than good. So we need to characterize the points that are out. Ideally we want all points to be within the epsilon sensitive tube, but when they are not, we want to characterize whether they are on the positive or negative side of the loss slope, right? So the loss on the last page was something like this, right? And we have C greater than 0 and C greater than 0. Right. So in the same fashion that we're writing out the SVM with soft margins, we can say, well, these are the total slack variables. The two norm W is the same. So, okay, see the book for how, like, the whole motion of basically going defining primal problem, the Lagrangian, and finally the dual problem. Let me say that. Let's not go through that in real time. And I think it's useful to look at the prediction function, right? So there are two sets of support vector weights now, alpha and alpha hat, and it still uses kernels, right? So the intuition here is the points that are inside the epsilon sensitive tube gets a support vector weight of 0, but points outside and on the border of the tube gets a weight that's greater than 0. That's all. That's pretty much all for today. So let me pause and say, Qinyu, in IML, you were taught the linear classifier with hinge loss. I'm afraid I have not looked at the exactly how IML covered the material. Let me say that, so that will, well, linear classifier with hinge loss will correspond to the linear SVM. I don't know if phi-x is there, but that extension is trivial. So if we check a hinge loss in there, does that necessarily yield a sparse classifier in, for example, a linearly separable case? If I can transform your question like that. So let me go back a bit. Hinge loss. I believe the answer is yes, because if this is, let me just write a question. Right, so if this is what's covered in IML, then it will yield the SVM solution. And the way to solve this is to, yeah, you can also do SGD, I think, because the flipped ReLU is somewhat differentiable. Actually, for quadratic programs, okay, there is one global solution. So SGD should find us the right thing. Yeah, I believe the answer to Tiny's question is yes. Because I've not thought about this rule beforehand, I'm not 100% sure. I'll let you know if I have to change my mind. I hope that's enough. Yeah. Yeah, so SVM expresses this thing in kernel space. And the variables we solve are the alphas, not the W's. But if we have the feature space, or if we're just dealing with linear kernels, we could just SGD this. Right, in practice, if you do like before the age of AlexNet, or basically the 2012 paper that used deep networks to solve ImageNet to do ImageNet classification, the de facto tool of image classification was to use SVMs on what's called hog features or some other like features. Unfortunately, for things like images, for those of you who are interested in computer vision, more than 60% of your data set end up being support vectors in a lot of cases. So in those cases, training support vector machines are slow, and it's not very sparse. Like if I have a, I don't know, 500,000 data point data set, my number of support vectors is like more than 250,000. That's not great. Computing it, training is slow, doing hyperparameter search is slow, and like doing prediction is also somewhat slow. It can be parallelized because one good thing about SVMs is that because of the, well, it's just a weighted sum of, what is it? Right. So this thing is a weighted sum of kernel values. It's embarrassing in parallel. So in terms of computation and so on. But right, so as that's also sparked basically interest in optimization community to develop better solvers for SVM, which we were sort of skipping in this slide, which I think, right, the effort spending on SVM is certainly not wasted. They are good. The kernel view is useful for understanding the behavior of very wide neural networks. So I would also say that kernel SVM is still one of the de facto practical machine learning tools, right? If let's say you're a data scientist or if you go to a data hackathon and you need to build a regressor or classifier, you should try, right, basically the few things, right? SVM, logistic regression or linear regression, and random forest or gradient boosted decision trees or decision stumps before you whack anything more sophisticated at it. And all of these are implemented in things like sklearning that you can just try out. With SVM, yes, you need to do rigorous hyperparameter search for that C. And remember, we talked about double loop cross validation. So that needs to be really set in practice well, because the trade-off is highly known. There are tricks though, so you could scale the data and so, for example, one most commonly used kernel for SVM is the RBF kernel because it's so flexible. So once you have that, you then have two hyperparameters, the C and the width of the RBF kernel, which you need to jointly search, which is a two-dimensional grid, right? If you're trying 10 data points for each, then it's like you need to train 100 SVMs before you have an idea about which hyperparameter values you should choose. Yeah, there are heuristics for choosing those. For example, your kernel width shouldn't be too wide or too narrow compared to your data, right? So first normalizing your data and then pick the kernel value that are sort of certainly below the 90th percentile of your pairwise distances, but maybe above a low percentile of the pairwise distances. That will give you the range to search. So this is the practical run of what you actually would do. And none of the textbooks have these written down. Some of them are sort of scattered around the web in blog posts. And none of it is super difficult to actually obtain. For example, how to set the kernel width. But someone just needs to have thought through it. And one really common, I guess, pitfall that I've seen in like graduate students and undergrad students doing a project is when they report a machine learning result, the like hyperparameters are not well thought out and they haven't been searched properly. So this is the practical ret. Right, okay, so Qin, you have another question. So SVM's kernel version of that, and the drawback of SVM, well, in the linear model, we can see which feature is important. In SVM, we can see which training data point is important. So yes, no free lunch if we want to, like, because in SVM the feature is implicit, even if there were feature importance indications, it's implicit, right? We can't get it. But on the other hand, we get the training data importance. On the other hand, if we use linear SVM, which are still used a lot with high dimensional sparse features such as, like, I don't know, your behavior on Facebook, yeah, we do get back the W, and they intuitively tell us something about whether a feature is part of the final decision or not. So here's another practical rant about the feature weights are not necessarily indicative of the feature importance. That's because in a linear classifier, two features could be like, imagine two features are actually just linearly scaled version of each other. Then the feature weights in front of them are actually just one weight, like sort of broken down into two parts. If we increase one weight, then the other weight should decrease, and they're essentially redundant. Right? That's the reason why they're not like interpreting linear regression weights or linear classification weights as is a faulty practice that I've seen people do all the time in papers, and I'm still like super uncomfortable about it for good reasons. But there are many other ways of measuring feature importance. Like if you do, I think you do, if for people who do proper statistics or social science, you can do basically, you can identify the most important feature with the largest R square. And then remove that feature and look at the rest of the features. I think that is a valid approach. There are many other measures. For example, the mutual information measure we talked about can be used as a feature importance measurement. Pearson correlation can be used as a feature correlation measurement if we're doing linear classification anyway. So there's that. There is no more questions. I guess I've ranted at you on the chapter 7 content and beyond for long enough. Yes, we're working on your assignment 1. There has been about 100 and almost 180 submissions, and there's going to be a few more that comes late, which means maybe say more than half of the class is working with each other, and I hope you guys have enjoyed collaborating. I also know that collaborating with someone else on an assignment can also be challenging. So there's also a reminder that Alex Sohan reminded the tutors team that students, some of them may not have set the teaming information correctly. If that's the case, scream to the tutors on Piazza, and we'll try and fix it before it's graded. All right. Otherwise, see you after Easter. Bye. Enjoy your break. Okay.
questions from students. Yeah.